Alright team, it is absolutely critical that you get a 100% straight exactly how to interpret test statistics. To do this, you'll be looking at the p-value, or the probability level, of your test statistic. You'll then be deciding if the result is significant, and then finally you'll be deciding what this result means in terms of either rejecting or accepting the null hypothesis, and by extension whether you have support or not for the alternative hypothesis. This process of these steps should be automatic, so you're not guessing which way to go, but rather going step by step and knowing that you're exactly on the right track. First, let's talk about p-values. As you now know very well, every test you run has a p-value that is associated with the given test statistic. When interpreting this value, you're always interested in whether the p-value is less than or greater than 0.05. Why is this the case? What is it about this magic number 0.05? Well, the answer is that this level of chance, i.e. something happening only 1 out of 20 times when it should be equal, or about 50%, is the criteria by which most biological studies determine as being pretty unusual. More specifically, you're saying that the observed result isn't due to just random chance, but rather because there is a significant difference or a significant relationship, depending on which test you're actually doing, occurring in the study that you're looking at. So the key thing that should be imprinted in your brain is a p-value less than 0.05 is significant. This line should be blinking in fluorescent letters in your head when you sleep at night, when you eat your breakfast, and of course, when you take your final exam. Now we've got p-values sorted, you've still got some thinking to do, as you need to know what it means to be significant. There are two parts here. The first part is simple. If you have a p-value of less than 0.05, you will reject or accept the null hypothesis. Think about it, and hopefully you will have decided to reject the null hypothesis. The second part, however, is a bit harder. You must know what the null hypothesis is for the given test that you are undertaking, as this is the only way that you'll know what you're actually rejecting. It sounds simple, but it's really important. We've undertaken many tests this semester, including ones related to statistical assumptions also. So let's quickly look at them all. So here they are, all the tests that you need to know the null and alternative hypothesis for. We've got the Shapiro-Wilks test, and we know that this tests normality. The null hypothesis is that the data is normal. So rejecting the null, i.e. having a p-value of less than 0.05, means that the data is not normal. The Bartlett test looks at equality of variance. The null hypothesis is that the variances are equal, and so rejecting the null means that the variances are not equal. When you've got two samples only, or are comparing just one sample to a reference value, and are interested in determining differences, we covered 6 tests that did this, including t-tests, Mann-Whitney U-tests, paired tests, and a one-sample t-test. In each of these, the null is that there is no difference between the samples, and the alternate is that there is a difference between the samples. However, you know that when asked to state the null, make sure you include as much detail and specificity as possible. When you've got 3 samples and 1 factor, we moved into one-way ANOVA. There were 3 different versions, i.e. one-way ANOVA, Welch's, and Kruskal-Wallis, but the null hypothesis of no difference between the levels of the factor was the same for each. When adding in a second factor, for a two-way ANOVA, we studied just one version, but, and this is why the asterisk is there, please remember that there are 3, not 1, null hypotheses, and of course there are also 3 alternate hypotheses also. This is the only test we did that has more than one null hypothesis, so please plant this small caveat firmly in your brain. Towards the end of the course, we began to test relationships via correlation, regression, and chi-squared. Again, each of these has their own null hypotheses of there being no relationship or no association. The alternative is that there is a relationship or some kind of association. In the case of goodness of fit tests for chi-squared, you're testing against whether proportions match ones that are given or are equal versus an alternative of the proportions not fitting as expected or occurring or not occurring in roughly even proportions. Anyways, you must know what the null and alternative hypotheses is for each of these tests. If you're listening to this and realize that you're not sure about it, why don't you take this opportunity to make a table that lists the null hypothesis and the alternative hypothesis for all of them. Such a table will be an excellent and important piece of information for you to review for the final.